Today, I have been invited to deliver an expert lecture on multirate digital signal processing, followed by the development of wavelet basis functions, their historical perspective, then applications. In particular, we should restrict our discussion to the application area digital signal processing, wavelet application to DSP. Otherwise, wavelets have several other domains of application areas. I must restrict my discussion to digital signal processing techniques, particularly for signal analysis and synthesis, how wavelets are useful. Before that, we must know all the basics of digital filtering techniques. We must know different types of digital filters. You should have adequate knowledge in different types of digital filters, that is FIR filter and IIR filters. We must know what are the differences between the digital FIR filters and digital IIR filters. FIR filters, I mean finite impulse response filters. IIR filters are otherwise known as infinite impulse response filters. There are some basic differences. Until unless you have adequate knowledge on the design and characteristics of FIR filters and IIR filters, you cannot understand the topic multirate digital signal processing. The reason is quite obvious. Here we are using either FIR filters or IIR filters for rate conversion. Rate conversion, I mean the sampling rate conversion. So, in this connection, we are forced to discuss a little bit of sampling techniques. Sampling is must in digital signal processing, otherwise it is really difficult to analyze different signals. It is really difficult to go for the communication, it is difficult for a conversion, it is also difficult for compression. Signal compression is an area of current interest, where this particular technique known as multirate filtering techniques or multirate digital signal processing techniques are useful. Multirate digital signal processing techniques are very useful for signal compression. Therefore, we should have some knowledge on the sampling of discrete signals. Analog signals are different, discrete signals are different. So, we must know the different types of digital filters, their characterization. FIR filters are known as finite impulse response filters, they are otherwise known as all zero filters. We do not have poles. If you can characterize the transfer function corresponding to a digital FIR filter, you will be able to know that there are only zeros, no poles in the transfer function. Let H z be the transfer function of a digital filter. So, H z can be expressed as a ratio of say P z upon Q z, where P z is the numerator polynomial and Q z is the denominator polynomial in z. If I can factorize the denominator polynomial Q z, I will get some poles. If I will factorize P z, I will get zeros. So, when there are only zeros, but we do not have any poles, then we can call the filter as FIR filter. And the other interesting property of a digital FIR filter is that FIR filters are more stable. Rather, I should say they are always stable. Of course, some conditions are there where they may also behave as unstable filters, but they are mostly stable filters as compared to the IIR digital filters. On the other hand, we have IIR digital filters which are not stable, they are always conditionally stable. You have to apply some condition so that IIR filter can behave as a stable filter. Similarly, IIR filters are otherwise known as all pole filters. They have only poles, no zeros in their transfer function. Let Hz be the transfer function of the same Hz may be treated as the transfer function of a digital IIR filter. In that case, if I factorize Qz, I will get only poles. If you will factorize Pz, you can find that there are no zeros in the transfer function except origin and the infinity. There are some other differences also. Number 3 difference is like this: FIR filters are known as non-recursive filters. They are non-recursive in nature. So, the computation time is more as compared to the counterpart your digital IIR filter. Digital IIR filters are recursive in nature. So, the computation time is less, therefore, they are computationally efficient. So, where the execution time is an important factor, we must go for implementing digital IIR filters. Similarly, the situation here in multirate digital signal processing, we will be using FIR filters and IIR filters. Mostly FIR filters are used, although they are not computationally efficient. I will explain why. While talking about the multirate schemes, I will explain why FIR filters are preferable rather than IIR filters, although IIR filters are computationally efficient. But there are some reasons for which FIR filters are well suited for downsampling and upsampling business. I mean, for multirate digital signal processing business, FIR filters are more suited. Otherwise, in other application areas, IIR filters are more preferable, because they are computationally efficient and recursive structures exist. You can easily write down MATLAB codes for implementing IIR filters, because you know the recursive structures, they are there in MATLAB programming. It is also very easy to implement FIR digital filters. Implementation is very easy, but the execution time is more. Number of computations, additions and multiplications are more as compared to the digital IIR filter. The reason is quite obvious. Here, if you want to achieve a maximally flat frequency response, you have to increase the order of the FIR filter. Once you increase the order, means you are incorporating more number of multiplications and additions. As a result, the computation time becomes more and more as you go on increasing the order of the FIR filter to achieve the desired frequency response. However, I can achieve the desired frequency response with a lower order IIR digital filter, and we have other differences also. Number 4 difference is regarding the linear phase characteristics of a signal. Sometimes in audio signal processing, in speech processing, we like to use linear phase filters. So, our digital FIR filters, they possess this particular feature. A digital FIR filter can be used as a linear phase filter. Otherwise, digital IIR filters are more suited for different applications, particularly in wavelet applications we use IIR filters because of their reduced computation time and easy in implementation using recursive procedures. So, these are all about the simple features or properties of digital FIR and IIR filters. Then we should know actually how to write programs for different FIR and IIR filters. You can read some basic DSP books. There are so many books available. You can read, say, S.K. Mitra, Digital Signal Processing by Professor S.K. Mitra. There you can find this multirate digital signal processing concepts. He has nicely explained the concepts. Similarly, you can also follow the other books, DSP books, all recent editions, they have incorporated multi-rate digital signal processing techniques. But before you read this chapter, you are supposed to know the design and implementation of digital FIR and IIR filters. We must know how to implement a digital FIR filter. There are some standard methods by which you can design FIR filters. The number one and the simplest method could be the window based design approach. The desired frequency response can be windowed by a particular window function, or else you can choose the ideal filter frequency response followed by a window to achieve the desired frequency response. There are several windowing techniques are available again. There are so many window functions. You can choose any one window. Kaiser window gives us better performance since it has a additional control parameter. Similarly, recently we have suggested another window called the spline window, B spline window function, where we have incorporated two more additional parameters by which you can control the maximally flat frequency response. Maximally flat or MF digital filters can be designed by using a B spline window functions. I will explain later on what is a B spline function and how to use the B spline function for the design of digital FIR filter. Similarly, we have other functions Hanning, Hamming, Blackman, Kaiser and so many other window functions are available in the literature. Similarly, you can also take the help from the DSP toolbox. The inbuilt functions are already there in MATLAB also. With the help command, you will be able to know what are the different window functions available for the design of digital FIR filters. Similarly, we have some other methods for design of FIR filters like frequency sampling methods and other recent methods for design of FIR filters. Similarly, we have two standard techniques for design of digital IIR filters. One is known as the impulse invariance method and second one is known as the bilinear transformation method. These are the two standard techniques which are used for the design and implementation of IIR filters. Similarly, you are supposed to know how to estimate the order of a filter. That is an important task while designing and implementing digital filters, because you will be supplied with the specifications. The manufacturer may give you or supply you the desired specifications, and you have to design the filter according to their specifications. Your designed filter must meet the given specifications. So, for that situation you may have to first estimate the order of the filter. Suppose I am interested to design a digital FIR filter. To obtain the maximally flat characteristics or frequency response, I have to estimate the order of the filter. So, you should know there are some standard methods for order estimation. At least one method we must know to estimate the order of a filter. Once you can accurately estimate the order, then you will be able to design the filter to meet the given specifications. So, with these fundamentals we can start the topic multirate digital signal processing. The basic sampling rate conversion tools are: number 1, upsampler. Upsampler may be treated as a device. In brief, we can consider it as a device which is used to increase the sampling rate by an integer factor, say capital L. With the help of upsampler, I can increase the sampling rate. Similarly, we have another tool known as downsampler, which may also be treated as a device, digital device, which is used to decrease the sampling rate by an integer factor h z is equal to p z divided by q z. H z is the transfer function. Then I must explain the upsampler. Upsampler is used to upsample or for upsampling, to increase the sampling rate by an integer factor. First, let me restrict my discussion up to the integer factor only. Later on we can consider the fraction or fractional factors. So, first we must discuss the upsampling business, then I must explain the time domain characterization. An upsampler with an upsampling factor capital L, where L is a positive integer, develops an output sequence, say x u n, u subscript I have used to denote the upsampling business, with a sampling rate that is L times larger than that of the input sequence x n. The block diagram representation is very clear. Let x n be the input sequence, x n notation is used to represent the input digital sequence. Output is x u n, the upsampled version of the input sequence x n can be represented by this notation, so x u n. The upward arrow mark represents upsampling business, L is the integer factor. Upsampling operation is simply implemented by inserting L minus 1 equidistant 0 valued samples between two consecutive samples of x n. Basically, it is an interpolator. The upsampling operation is implemented by inserting L minus 1 equidistant 0 valued samples between two consecutive samples of x n. What you mean by this? Basically, upsampler is nothing but an interpolator. Interpolation, you know. What is interpolation? Estimating intermediate values from the given discrete samples to represent a continuous function. Estimating intermediate values from the given discrete samples so as to display or plot a continuous function from the given discrete samples. This is what I mean by the interpolation. So, interpolation play an important role in communication and digital signal processing. The filtering operation is basically an interpolation process, and in interpolation usually we deploy an interpolating function. You might have heard about interpolating functions in mathematics. There are so many interpolating functions available in the mathematics literature. The best one could be the B-spline function. You might have heard about B-spline interpolation. Similarly, we have Akima, Hermite polynomial, Laguerre polynomial, then Lagrange polynomial. So many other polynomials are used for interpolation. And the ideal interpolant is the sinc function, your sin x by x function is the ideal case, which we cannot implement in practice. So, always we are trying, or different researchers and professors, they have been trying to have a close approximation to the ideal interpolant, that is your sinc function. That is why as on today we have so many other types of interpolating functions, starting from the Legendre polynomial to B-spline functions. So, here also your upsampler is basically an interpolator. We are going to interpolate the intermediate values from the given discrete samples. So, first you have to introduce L minus 1 number of equidistant zeros to increase the length of the signal or samples. The input output relation is simply written like this: x u n the output from the upsampler, x n is the input sequence. So, it is simply x n divided by capital L, where L is an integer, positive integer, and n may be equal to 0, it can be plus minus L, plus minus 2 L and so on, 0 otherwise. With this figure, I can let you know what exactly we are doing when we are talking about upsampling business, or what is the role of an upsampler or an interpolator. The figure shown here will explain us how to really do or achieve this upsampling or upsampled version of the input sequence x n. This side we have the sinusoidal signal with frequency say 0.12 hertz, and let us assume that the upsampling factor is 3. Then the upsampled version of the input sequence x n has been shown here. Capital L is equal to 3, therefore, we have to introduce 3 minus 1, that is equal to number of equidistant zeros in between two consecutive samples. So, this figure will give you sufficient idea about the upsampling business. So, you can also write a program by applying your own logic. It is very easy to obtain the upsampled version of the given input sequence x n. First step is very clear. You can easily introduce L minus 1 number of equidistant zeros, that is otherwise known as the zero order interpolation. You might have heard in your mathematics or in communication. Sample and hold business is basically a zero order interpolation business. We are introducing L minus 1 number of zeros in between two consecutive samples. I think this figure is clear. Here you have 50 number of samples, frequency is 0.12 hertz. You can also easily generate this signal by writing a MATLAB code for this, very easy to generate. You know how to obtain these samples, discrete samples from the continuous signal with frequency say 0.12 hertz, very low frequency signal. It can be easily generated. Then I can also generate this by using this standard technique of sampling technique. In practice, the zero valued samples inserted by the upsampler are replaced with appropriate non-zero values using some type of filtering process. This is our next step. Otherwise, the interpolation business could have been very simpler and we need not read so many literature. By this time, we have seen more than thousands of research articles in this connection, because we do not want to introduce so many number of zeros in the upsampled version of the signal. You know the reason why. If you put so many zeros, then obviously we are losing some information. While retrieving the information, you have to lose some information. You can also verify with the help of MATLAB programming. Information retrieval becomes tedious when you introduce so many number of zeros. So, in this sense, here zero order interpolation is totally useless for different applications, may be communication, it may be image processing, it may be your digital signal processing. The simplest method is the zero order interpolation business. One can easily introduce so many zeros. Similarly, you can easily magnify an image. Now, you can understand what I mean by zero order interpolation. One can easily magnify an image. Even a class 4 or standard 4-5 student can easily enhance an image of size say 32 by 32. An image is given, size is say 32 by 32. I want to enlarge the image and make it say 256 by 256. How to do that? You can easily introduce 8 number of zeros by using a 2 by 2 matrix, so that the size becomes 256 by 256, because upsample factor is 8, 32 by 32 size image is available to you. You can easily make it 256 by 256 by introducing 8 cross 8 number of zeros in between two consecutive samples. So, what will happen if I enlarge the given image by using zero order interpolation? What is the problem? Can you guess what could be the problem? Useful information will be lost. You will be able to see some patches, repeated patches throughout the image. So, this way the visual perception is very bad. You may not like to see the picture, because the visual perception will be very poor and you may not like to see that picture. If you deploy or use zero order interpolation to enlarge the picture from a size of 32 by 32, a size of 256 by 256 with a zooming factor of 8. You can easily verify by using MATLAB programming. You take one image, small image of size 32 by 32, deploy this particular technique, you see what happens. Some information will be lost, and particularly you will lose the high frequency components, the sharpness of the image will be lost, you may not like to see the image. So, what to do then? You have to think for some other interpolation techniques. Then we have first order interpolation, the improved version is the first order. Then we have quadratic interpolation schemes, then we have cubic interpolation like cubic B spline interpolation scheme. So, there are several other interpolation schemes which are very useful for interpolation. Similarly, here by simply incorporating number of zeros L minus 1 number of equidistant zeros, we may not get the better upsampled version of the input sequence x n. Our objective is different, we like to estimate the intermediate sample values from the given discrete sequence x n. How best we can estimate the intermediate values from the given discrete sample values is very important. Our objective is clear, we have to efficiently estimate the intermediate sample values. So, for that we have to use some filters. We have heard about low pass digital filters. So, by using low pass filters, we can estimate the intermediate sample values. Your low pass filter is basically an interpolator. And the interpolant is the basis function by which you have developed the particular FIR low pass filter. Suppose I have used a B spline window function to design and implement a digital FIR low pass filter. In that case, the interpolant is the cubic B spline function. So, the underlying principle must be very clear. When you design a digital FIR filter, you should know the underlying principle by which you are going to design, and what is the basis function by which you are able to design different types of window based digital FIR filter, that is important. So, whatever filtering theory you are reading, this is all interpolation business. Whatever we are doing in engineering, they are all interpolation and approximation. Mathematics people, they know it in a better way. Actually, for mathematics people, it is all interpolation and approximation. Interpolation I have explained, you know what is approximation. They are all same, except only one difference. The interpolating functions, they are restricted or more constrained to pass through all given data points, and that restriction has been lifted for approximating functions. The approximating functions need not pass through all the given data points. They may pass very close to the given data points, not exactly through all different data points or discrete samples. This is the only difference you might have studied in your mathematics. So, for DSP people also it is all interpolation and approximation. Wavelet theory, the underlying principle for the development, responsible for the development of your wavelet theory is approximation theory. So, you must know the approximation theory very clearly, otherwise we may not be in a position to understand the wavelet and their applications. Here upsampling business is your interpolation business. So, you should know exactly what interpolation is. If you can understand interpolation, then you can easily understand the sampling rate conversion. It seems very easy once you know the interpolation business. So, here in practice we never want to introduce so many zeros at the output of an upsampling device or upsampler. The zero valued samples inserted by the upsampler are replaced with appropriate non-zero values using some type of filtering process. This filtering process means we are again using some interpolation schemes to replace the zero valued functions by some non-zero valued or appropriate non-zero valued values using some filtering process, and this process or this filtering process is called interpolation and will be discussed later. Thank you all.